Hey y'all. Okay. Today is Monday, October 25th. A couple of exciting-ish developments. One, next Monday is mini exam 4. It covers lectures 16, 17, and 18. So that is last Wednesday, today, and Wednesday. Just those 3. So it will cover Hess's law and heats of formation from chapter 5 and whatever part of chapter 6 we get through this week. Likely, not all, it will take a miracle for us to finish the whole thing. Miracles have happened, doesn't feel super likely today, but that's what that is. Your Chem and Life is due Wednesday at the start of class. 20 points, 300 words. It must be a single PDF. If you do not know how to make a PDF with the picture embedded or merge them together, please do that. Questions about mini exam 4 or Chem and Life 2? So, starting today, some very exciting things are going to happen in your gradebooks. None of this will happen until I go back upstairs. So the plan is, I'm going to give you back your exams, then I'm going to go back upstairs, I'm going to upload the video to YouTube, I'm going to do all these gradebook changes. It will not happen immediately, but it is happening as well as the posting of scores. So, as I drop that giant bag, I do have your midterm exams here. We are getting them back at the end of class today. So, per the syllabus, the lowest 2 Alex weekly submission scores will be dropped. That goes into effect in Canvas starting today. So you should see them. On my end, they turn orange. They may turn a different color in yours, but they will gray out. For the mini exams, the syllabus says that the lowest 2 mini exams will get dropped. I'm going to start dropping the lowest 1 today. We'll add in the second one after we get closer to mini exam 5. Basically, I want to give you the most realistic impression, but you should make the assumption that you will make a 0 on 5 and 6 in order to, 1, continue to study and all the rest of that. It's not on here, but the other thing that's going to change starting today is your letter grades. So right now, if you look at your Canvas gradebook, it says like S or U. Starting tonight, after, I'm going to do all these, it's going to happen in a while. By 6:30, that's how long I think it should take, what you will see is your S and U convert into whatever the corresponding letter grade is. So in my class, an 85 and above is an A, 70 to 84.9 is a B. There's some pluses in there, no minuses. A C score goes between a 58 and a 69.9, a 48 to a 57.8, no, 57.9, whatever the next value of that is a D. If you have a below 48%, that is an F. Now, many of you in here are not first-time in college students. Most of you have been around a while, but I do want to remind you if you are. So in college, your transcript just has letter values. So if you score a 65 in this class, a 65%, that is a C+. No one but you and me, and I'm going to forget as soon as I publish grades, will ever know that you had a 65%. Your transcript will just say C+. We'll all go on about our merry way. So that's how your transcripts will work. So that letter grade corresponds to that. So whatever values, if you have missed a mini exam in the past, it should be a 0 in the gradebook in order to make it drop it. So if you've missed one and you saw that I gave you a 0, it was in preparation for this instance. Any questions about the gradebook changes, the previous announcements, any other, I don't want to call them life questions, any other topics of interest today?
Is the chemistry and life 1 grade already in, or are you putting that in?
Are those posted? They are posted. I was like, I posted those, right? You're giving me a nightmare that somehow I graded them and they've all been in grade limbo. No, those just took longer because somehow, frankly, they fell off my to-do list, and then I looked at it and I was like, oh my God, I need to grade those. So it should not be as long of a delay for the next ones. But it's basically, can you write the right number of words, embed everything in the right thing, and is it chemistry related? how many of you have started your well, you only have one objective due tonight. How many of you have finished said objective? Okay. So, some of you, I've gotten a number of emails and a number of questions. So, we talk a lot about how Alex likes to go cuckoo for Cocoa Puffs. So, we need to go to St. Augustine. We can get on 95 and drive south for like 45 minutes and you're there. Or, you could drive to Alaska and then get to St. Augustine, right? Alex would like you to go to Alaska first, which is fair. That is a valid way to get where you need to go. I would strongly suggest that you not take that route. So delta H reaction is the sum of the delta H naught F's for the products minus the sum of the delta H naught F for the reactants. So, Alex gives you a couple of interestingly irrelevant data points. Alex likes to show you, so these two equations on this slide where it says CS plus O2 gas gives you CO2 gas, and then we have a delta H equals negative 393. Okay, this is a heat of formation equation. This equation is where this value comes from. So a heat of formation is to make 1 mole from its parts. So if you look at the second one, where it's, that one doesn't work. The top equation where it's C solid plus half O2 goes to CO. That is to determine the delta H naught F of carbon monoxide. We did this example using Hess's law, right? Where you manipulate the equations. So you can do a very long, drawn out, very deep calculation to prove that Hess's law and the heats of formation give you the same answer. I opted to skip that because in the end, what we all realize is the shortcut works. So the shortcut is that we could use the heats of formations, the sum of the products, minus the sum of the reactants. So Alex gives you these equations and these values, and then it starts to say things like, make sure you assign the sign correctly. I hate remembering to assign the sign. If you do it this way, products minus reactants, you don't need to remember who's positive and who's negative. It's done in the calculation. The biggest thing you need to remember is, if we have two things, it's 2 times delta H not FA plus 3 times delta H not FB minus the sum of the other parts, 2 times delta H not F of E plus delta H not F. If both of these are negative or positive, make sure that you sum them together. So my recommendation would be to do this calculation. We'll say negative 125 minus negative 250. So this calculation gives you positive 125. My recommendation would be that you sum these up independently and then do the last calculation at the end. Or use like 9 times more parentheses than you think you need. Those are your two options. You can choose either one. Both will get you to the right answer. Does anyone have any questions about calculating delta H reaction using delta H not F? Super. Oops. There is one thing we'll talk about today where I will tell you how Alex is going to one-up or level up the calculation we're going to do so that when you guys go to do your objectives, particularly particularly in this chapter, which is the last super math-heavy chapter for a while, Alex sometimes likes to take weird detours. I would strongly recommend that you look at your notes for all these calculations because I will combine different elements into a single value, where Alex will be like, remember that this number comes from here, and I will just be like, oh, that all comes together and means negative 12, which is not a value, but you know what I mean. So, chapter 6. So, chapter 6 is an exciting chapter. Well, in my opinion, but I also teach this, so I think everything's exciting. So, chapter 6, we're going to start to think about the electronic structure of an atom. Hold, please. All right, now we're good to go. So, in this chapter, if you vaguely remember in chapter 2, long time ago when we watched those videos on YouTube where I talked and wrote, we talked about, okay, the atom is protons, neutrons, and electrons, and Rutherford determined that the center of the atom is the dense nucleus with the protons and the neutrons, and the electrons were scattered around, and then we stopped. And then we talked about equations and everything else. We are going back to the electrons to say, but where are they? So if you have, 1, read the textbook, or 2, taken intro or high school chemistry, you may know that electrons live in orbitals, such as the s orbital, the p orbital, the d orbital, and the f orbital. What we're going to do today is to get probably 85% of the way through the derivation of where those orbitals come from. I use the word derivation, and I feel like half of you internally crunched and were like, this is going to be the worst day of my life. Not like that. Mostly we're going to look at different topics. We're going to mush them together. We are going to end in a place where it feels like an odd cliffhanger, just so we're all aware. We're going to kind of end, and it's going to be the messy middle, like when you're cleaning a room and everything's a mess and it's never going to work. Bear with me till Wednesday. It will all tie up. It will be a beautiful story. We just can't put it all in 75 minutes. I say that now because I feel like in about 50 minutes you're going to be like, are we ever going to get to the end? We will. I promise. It will be a great place. But we're going to start looking at that. If you read along in the textbook, these readings underneath correspond to the subsections in chapter 6. I basically combine different parts to make them more of a complete story. So there's 4 discrete elements. My guess, if you would like my uneducated guess, is that we will finish 6.3 for the mini exam 4. We will not finish all of chapter 6 for that. That is my today guess. We will talk about 6.1, 6.2, and 6.3. So before we can talk about electrons, we have to talk about how we figured out where the electrons were. We're going to use light. So as we talk about this today, when you go to Target or Amazon or wherever it is you buy light bulbs, most of us buy what I like to call fancy light bulbs. All of this research is done with the old school light bulbs with a filament inside, some sort of a sketchy light bulb that isn't all that cool. That's how this research was discovered. It doesn't work as well with LEDs. LEDs have different wavelengths of light. They don't tend to emit in the exact same ways. So if you were to do these experiments at home with your LED light bulb, it might not work. If you can find the old kind that are very hard to find, because Target doesn't sell them anymore, then it will still work. But today we're going to talk about light, and light in terms of a light bulb. And so as we start to think about light, it's important to be able to think about the spectrum of light. So light has many wavelengths and many frequencies. So when we see a visible light, it's type of electromagnetic radiation. So the first thing we want to think about is the wavelength and the frequency. So if I draw where we have time, we have amplitude, we can draw a wavelength of light, or a wave. So in this case, if this long line is our period, basically how long of time we're going to look at, there's a couple of things we can think about. The wavelength of light is the peak-to-peak distance. So this lambda symbol stands for wavelength. This is the length of a wave. And it determines the color of the light. And so it's the length of a wave. In this case, I'm looking at peak to peak. You could calculate the wave point as peak to peak, trough to trough, midline to midline, as long as it's the same place in the wave. So you could go from here to here. I'm not an artist, which we all already knew, so these are not perfect. This is just a wavelength. So the other thing we're going to think about is, so the units here are meters. The other thing we're going to think about is frequency, which is mu. So that's the frequency. And frequency is how many cycles are in a certain time period. So if this value here is our time, for this one, we have a frequency of 2. That means there are 2 full cycles in this given time. So the units of frequency are basically cycles per second, which often is 1 over s. If you want to get super fancy, they write it as hertz, not the car rental, just the scientist, where hertz is 1 over s. So what per second and hertz are the same unit. They are a 1-to-1 conversion between those. So the best way to really think about the difference between frequency and wavelength, or how they interact, is to look at 2 different waves on the same plot. So we now have the red line and the black line. Hopefully you guys can see. So the frequencies, if I did this right, the wavelength of the red line is roughly half of that of the black line. Give or take, please don't use a ruler, I just did my best. But if you look at the red line, there are twice as many cycles in the same given time period, right? So basically we can see more red humps than black humps, and it basically is twice as many. So this is going to start to tell us that the frequency and the wavelength are interwoven together. Frequency and wavelength are basically tied together in a way that as one increases, the other decreases. Any questions, or what questions do we have before we move into how these 2 values are connected? So light, all light, moves at the speed of light. Fast light, slow light, all of it interacts at the speed of light throughout the entire electromagnetic spectrum. So the wavelength and the frequency, the wavelength multiplied by the frequency is equal to c, which is the speed of light, which is a constant, and that value is 2.998 times 10 to the 8 meters per second. This equation and the speed of light constant are going to be found on your equation sheets. I'm going to try to highlight all the different things that will be found on your equation sheets. Chapter 6 adds a lot of constants, a lot of equations. Just so that you're aware, they are forthcoming. All of them will be in there. So the speed of light is a constant, 2.998 times 10 to the 8th meters per second, where the meters times the per seconds gives you the units of meters per second. So we can, if we are provided either the frequency or the wavelength, we can calculate the other through the speed of light. For example, what is the wavelength of light in meters and nanometers emitted from a bulb with a frequency of 8.18 times 10 to the 14 hertz? So just like in chapter 5, we read the question, we have a moment of panic, we write down what we know. Once you do that, you can say, okay, I'm going to look at my equation sheet. What do I have that could be useful? So in this case, we have a frequency which equals 8.18 times 10 to the 14 hertz, which is also 1 over s. And so we know that c equals lambda nu, and so we are solving for the wavelength, which is the speed of light times the frequency. The speed of light is a constant, and that gives you 2.998 times 10 to the 8th meters per second, divided by our frequency of 8.18 times 10 to the 14 hertz, which is a per second. When you do that, the seconds both cancel, and now we have 3.67 times 10 to the negative 7 meters. And it asks for this value in both meters and nanometers. So, does anyone remember how many nanometers are in a meter? 10 to the 9th. If you said negative 9, you're also right. It's just where you put the equation. So in 1 meter, there's 1 times 10 to the 9th nanometers. And so that gives you 367 nanometers. What questions do we have about this calculation? Yes?
So how many meters per second? That's because it's in the equation for speed of light, right?
The speed of light,
The as divided by s, that's meters per second, right?
this right here, is m divided by s, so meters per second.
Thank you.
Yeah, good question. Other questions? We're going to do more of these calculations. They're kind of interspersed all throughout today. So the next thing we want to think about is the energy of a photon. So some objects this next part gets a little dodgy, but we're going to struggle through it. When we heat certain elements, they give off light. If you put metal into a fire, some of it gives off light, not all of it. Some metal glows when it is, basically light just shines upon it. You shine a laser on certain things, it will glow, but not always. So when this energy is released, so energy is released, as we learned in chapter 5, as heat or work. One of the other ways that we can release energy is as light. And this energy can be released as light in the forms of this equation where E photon. Does anyone need this information? Excellent. Where E, in this case, is the energy of a photon. So they were able to measure this light that comes off, single photons of light, and basically say, Okay, the energy of this photon changes. And we can measure that, and we determine that it is relative to the frequency by a value called h, where h is Planck's constant. And it is 6.626 times 10 to the negative 34th joule seconds. Both this equation and this constant also found on your equation sheet. So Planck's constant basically gives us the relativity, or how it adjusts. So every wavelength of light has a different energy of photon, or the energy of that photon is different.
It doesn't really matter in terms of like finding the answer, but it's interesting like what's happening here is different for a degree. I noticed that it says joules seconds, not joules per second, like I might have seen like a wattage. What does joules seconds look like?
That's a unit.
Yeah, I get that, but it's joule seconds as opposed to something that I could easily understand like more easily like wattage, which is joule per second. So what is a joule second look like?
I can answer that.
Excellent.
Well, it's because your frequency is in seconds to the negative 1 to the power of negative. It's 1 over a second, so then your seconds cancel, so then it's just in joules, which is the form of energy.
Okay.
So it's seconds cancel.
Thank you. I was like, I don't know. It's a constant. It's just what it is. But he is correct that the energy will just be in joules. This allows you to equilibrate between those. And so Planck's constant is made up of several other constants. So where do these, and how did we determine that light has these photons of energy? So over time, it was realized that this energy, these photons, were in discrete packets. Those packets are called quanta, and quantas are basically teeny tiny little light bits. And so they are discrete bits, and so the energy goes from E to now EPH to make it the energy of any given photon. And they are related to one another through Planck's constant. So the way that we discovered this is through what's called the photoelectric effect. So some metals, not all, when you heat them, give off light. One thing we know, depending on how your life goes, is when you put metal in fire, it takes a little while for it to start glowing. You have to heat it up to some point. You have to put in enough energy in order to overcome some barrier. And after that, your metal is going to glow. That barrier is something called the work function. And the work function in this equation is EK. Well, EK is the kinetic energy equals the energy of the photon minus the work function. How well tightly packed or how ordered your metal is changes the work function. So the work function is a constant value. Work function values come out of a table. They are the same. Once you overcome that, you're going to basically spit out photons all day long until you remove something else. So these electrons are going to be ejected with with the same energy. So what this means is if you have metal, as you irradiate in, you're going to irradiate out at the same energies. Just one will be positive, one will be negative. So in this case, the electrons are going to be ejected based on the wavelength of light. Or the wavelength of light is based on the electrons that come in. All of this is to help us think about one thing. Light can behave as both a wave and as a particle. Not today, but definitely on Wednesday, we are going to learn that electrons can behave as a wave and as a particle. And the reason this is important, here's twofold. One, it's going to help us think about how these energetic packets interact with one another. And two, some of you are engineers, or want to be engineers, hope to be engineers to be. When you start to think about the development of different products, whether it is in energy transmission or solar generation or anything else, these work function calculations tell you about the efficiency of different compounds. So I present this to you as a reminder that chemistry is much broader beyond just, here's an electron, here's what it does. This calculation we will not do, so the EK equals the work function. This is more of a presentation than a calculation. We are going to calculate the energy of a photon, and at the end of lecture, I think we'll start to calculate how the energy of a photon interacts with the energy of an electron and what those two look like. But all of that work is based on the photoelectric effect. So in order for the electrons to be ejected, once they are hit with a photon of light, the photon has to have a particle behavior. When we think about light, it refracts. Refraction is not a particle behavior. So the rainbow effect, if you have like a sparkly diamond or pretty stained glass in your window, that rainbow effect is due to the wave nature of light. If you use a laser diode, I don't know, in like a weird security system, that utilizes the photon effect or the particle behavior of light. So both of these are true. So light behaves I'll get that. But I was pretty sure it was dead earlier, and I kept using it, so light behaves as both a particle and a wave, but never at the same time. So one of the things we've noticed as scientists is that the wave behavior of light is different than the particle nature of light. So light can be either a wave or a particle. But I will admit, when I first started learning about this, I thought it was a wave of particles, that it basically moved along. It is either a wave of light or a particle of light. It can shift back and forth somewhat instantaneously, but you get both behaviors, but not at the same time. So this asks us to calculate the energy of one photon of light, one photon of yellow light that has a wavelength of 589 nanometers. Oh, good. This equation's already here. So we are presented with a wavelength of light of 589 nanometers. It's the only data point we have. And we know that the energy of a photon is Planck's constant times the frequency. We can calculate the frequency using the speed of light. So we know that the frequency is equal to the wavelength times, the speed of light equals the wavelength times the frequency. Now, there are two ways you can approach this question. One, you could solve for the frequency, plug it into the photon of light equation. I prefer to use my calculator once, so I'm going to manipulate these two equations to make a new equation. So I'm going to solve for the frequency here. So frequency equals the speed of light divided by the wavelength. And I'm going to plug this value in here, where the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength of light. What questions do we have, if any, about this manipulation of equations? Yeah?
So how do we know which equation we're essentially using?
It's a good question. So it asks you for the energy of one photon of light. So the photon of light equation is E photon equals Planck's constant times the frequency. But we're only provided the wavelength. So that's why you have to use both. If we had given you just the frequency, you could just plug it in and move on with your life. Other questions? So from here, we're basically going to just start plugging in numbers. So Planck's constant is 6.626. 10 to the negative 34th joule seconds, multiplied by the speed of light is 2.998 times 10 to the 8 meters per second, divided by, in this case, the wavelength of light, which is provided in nanometers, so we need to convert that to meters. So 589 times 10 to the 8, 10 to the negative 9 nanometers, and that gives us 3.37 times 10 to the 19 joules. What questions do we have about this calculation as it is currently written? Yeah?
So with like the V, when you like manipulated the equation, like where did V go into the new manipulated equation? Like they like circled V and like put an arrow out. I'm just lost on like where V like went.
So the frequency is equal to the speed of light divided by lambda. So I plugged in these two values into this equation, and that gave me this equation. Other questions? Yeah. So in this case, I manipulated the two equations. So we know that the photon of light, the energy of a photon, is Planck's constant times the frequency. We're only provided the wavelength. So I solved for the frequency in the speed of light equation, where nu equals the speed of light divided by lambda, and then I plugged in these two values in here.
So you've already done the calculation, so just been write it down, is that what you're doing?
So I opted to, so there's two ways you could do this. And I didn't write this other one down, so I'll just kind of mock it out for you. So you could have done this in two steps. One, solve for the frequency of light with 2.99, C over lambda, which is 2.998 times 10 to the 8 meters per second, divided by 589 times 10 to the negative 9 meters. So that would give you the frequency. Then you could have plugged whatever value you get here into the energy of a photon is equal to Planck's constant times the frequency. So I basically, instead of stopping my calculation here, just realized that, oh, I can just put this part in here and took this whole thing and put it in here to only have to do a calculation instead of two parts. You could do this in two parts. It's really a one-stepper or a two-stepper. There's no other alternatives. I'm sure there is, but I'm only showing you these two. Any, yeah?
Could you explain to me why you converted from nanometers to meters?
Yeah. So the question is, why did I go from nanometers to meters? To get rid of this meters. You could have left it in nanometers, but then your units on this would have been joules times meters over nanometers, which is not a real thing. You could do that. It would be wrong. But that's why I did it. Oh, great question. Yeah.
What's for the symbol V again? Because I have C as speed of light and then the frequency is underneath it. So what's V?
V is nu, which is the Greek letter nu, but like mine look like these. So it should look like a, do you see at the bottom here, this V with like funky, flowy edges? That's all it is. Mine just look like these. I can't make it look like that. So Alex is going to ask you to do this, but more. So Alex is going to actually ask you, instead of calculating the energy of one photon, it will ask you to calculate the energy for a mole of photons. So this is the joules per 1 photon. So you can actually just multiply that by 6.022 times 10 to the 23rd photons per mole. And that's how you could convert the energy of a photon into the energy of a mole of photons. There are other objectives in this objective pool, but this one tends to historically give students a little tricky. Any other questions about calculating the speed of light's constant? The frequency, the wavelength, or the energy of a photon? So we've talked about this, and we have talked about our ultimate goal. Our ultimate goal is to determine where the electrons live. So this next section, where we're going to look at two scientists, the Bohr model and the de Broglie equation, these two are going to really start to think about how light and electrons interact with one another. How do they interact? What does it mean when they interact? And where do they go? If you printed out the slides, and like this one, you're like, oh, Dr. Malcolm forgot to include the words. There are no words. I'm going to draw all over the board, and you will write next to those slides. At the end of the chapter, there are a bunch of slides that have almost nothing on there. That's a place for your notes. There's nothing missing. That's just what they look like in this chapter. So line spectra. So before we think about what is a line spectra, let's think about where that came from. So if you have broad spectrum light, which is code for like any light bulb that you've ever encountered in your life, that isn't a like thousands of dollar light bulb. So the regular light bulbs in your house, the light bulbs in your bathroom mirror, even most LEDs, if they're not colored, so colored LEDs are a little different. But we're gonna have a light bulb. That's a little like a light bulb. So we have a light. And out of this, we are going to get different rays of light. From there, we are going to organize them through a slit. And then those organized light waves are going to go through a prism. And once they do that, we are going to get a rainbow. And so this rainbow is the same rainbow that you have probably seen your whole life. When something sparkly or any prism you encounter gets hit by organized light. Now, the slit here is an organizer. Basically, it allows all of the light to get in the same order so that when it hits it, you can see it bending. So if you look at prisms that you often encounter, like crystals in your house or different stained glass, it doesn't always make the pretty rainbows on the wall. That requires the light to be at a specific wavelength or at a specific direction. This basically just organizes all the light to where only some of the light gets through. When that happens, that ordered light basically bends into this absolutely exquisite rainbow. So this rainbow is observed in broad spectrum light. If you were to have a green LED, or a blue LED, or a purple LED, you would not get all of these colors. You would get some things, but it would be based on the light that you started here. Before LEDs, in the way back zone, you could buy light bulbs that were filled with different types of molecules. So these are still things. So neon lights, I don't know, if you go to like any restaurant and they have a beer sign on the wall, it's usually always beer, maybe not an open closed sign. Those signs are filled with neon gas. You put electricity into it, and they come off in different colors. What scientists did, because remember this is the way back zone, there's no Netflix, there's no internet, it was like boring land. They ran the same experiment, but with different types of lights. So they used a hydrogen light bulb, a neon light bulb, really any element they could get their hands on to make a light bulb with. And so instead of getting the rainbow for the hydrogen light, so instead of this for hydrogen, they only observed four spectra. So this is what's called a line spectrum. So in that graphic, the dark parts are that there is no light shown there. So instead of seeing this broad spectrum of a rainbow, what we see is we only see specific emissions at 4 discrete energy levels. And so in the graphic underneath the hydrogen, that's the neon light bulb. So now they have more transitions, but they are clustered somewhat similarly. So as we look at this from the back of the room, it definitely looks like the red lines and the teal lines are kind of in the same place. But if you look all the way to the right on the hydrogen, there is no magenta or purple observed in the neon. So one of the main differences between neon and hydrogen has to do with the number of really protons, neutrons, and electrons. What we're going to come to find out is the main difference in the line spectra is solely due to the number of electrons and the number of transitions that they can make from one given state to another given state. And so we're going to look at how electrons move around inside an atom and what that gives us in terms of a line spectra. Questions? So around this same time, so we start looking at line spectra. Rydberg comes along and he goes, hey, you know, when we look at the wavelengths of light observed for the hydrogen line spectra, these fit together using an equation. So again, this is the olden days, there's no Netflix. People thought about how do these energetically interact with one another? And can we predict, or can we find an equation that allows us to figure that out? So the Rydberg equation allows you to determine the wavelength of emission only. So this is a prelude to the next equation. So unless the question specifically asks for emission, the Rydberg equation doesn't work. It will give you the negative of the answer, and there's no negative wavelengths. So in this case, it's 1 over lambda equals the Rydberg constant, which is provided below, 1 over n1 squared minus 1 over n2 squared. And this only works where n2 is greater than n1. So basically, what we're going to look at in a minute, it only works when an electron falls from higher energy to lower energy and gives off energy. So the Rydberg equation is good, and it was the first step to thinking about how this works. So when they started to consider, we're going to flip back for a second, to look at these two spectra, they started to ask themselves, why are they different? The other thing is the Rydberg equation doesn't actually work quite as well for anything other than hydrogen. That's going to be a whole theme in chapter 6, that they did stuff on a one electron system that it turns out is irrelevant or it doesn't work and gives you slightly wrong answers. So the Rydberg equation works for emission. So Bohr came along and wondered if these lines arise from electrons. Each element we know has a different number of electrons. So here's where we are in time. We have a nucleus and we have electrons. When we left Rutherford, he said they were out here like kind of all everywhere. So the Bohr model and the Rydberg model are basically trying to figure out where are the electrons in reference to the nucleus. So the Rydberg equation tells us that they're at levels, but they're spinning around the circle. Centrifugal force basically tells us that two things should basically spiral into one another over time, which is not what we observe for electrons. What we actually see is that the electrons live in these spheres, or layers is probably more accurate, outside of the nucleus. So we have these layers. And it turns out that these lines are going to be the movement of an electron from one layer to another layer. And it goes up in response to the energy of light that hits it, or it gives off light as it goes back down. So the Bohr electron model tells us a couple of things. One, electrons in an atom can only occupy certain orbits. These are going to correspond to these lines, and they correspond to certain energies. And so these electrons in permitted orbits have specific allowed energies. And that energy is not radiated. So basically, the electron lives in this place, and it stays there. And the more interesting statement is this third one. Energy is only absorbed or emitted in such a way to move an electron from one allowed state to another. So let's think about this in terms of maybe a better word picture. All of you came in here today, and you sat in rows. Each of you are in a defined row. If I just numbered them up, 1, 2, 3, 4, 5, right? All of you can choose to sit anywhere you want. But it turns out that you live in a discrete energy. It would be very difficult. This worked in my last class, so it definitely will not work here. You could set up a chair here on this row. You could sit here. This would be the most uncomfortable situation in your life, right? Or you would fall out. Well, maybe not. I would fall. I could last for a few minutes and I'd be like, this is the worst. I would either want to move back up onto the step or fully down. Electrons are the same way. There is no in-between. You are either on this level or the next. You either make a whole jump or you don't jump at all. So this is probably the most, not exciting, but it's an interesting facet of the Bohr model because he's trying to say, hey, when we think about the energy, do we see electrons moving from low energy to high energy? And we see them going back. So he's saying that electrons from row 1 could move to row 6, and those of you on the wall lining could move, although you probably won't, to the front row, right? You could, although all of you just started sweating and were like, hey, absolutely not. But you could change rows, but only in those discrete values. So for the hydrogen atom, and only the hydrogen atom, one of the things that he's trying to figure out is how can I calculate the change in energy that these electrons are going to see, or the singular electron. So the first thing he does is he figures out a couple of things. So in order to determine the energy states, he determines that n has to be a whole number. And so in chapter 5, I told you that it was very difficult to ever calculate energy at a specific time. That is still true, but Bohr makes a really good estimation in terms of the energy of an electron in an orbital. So he says that the energy is the negative hCRH 1 over n squared. If you multiply Planck's constant, the speed of light, and the Rydberg equation together, you get negative 2.18 times 10 to the negative 18 joules 1 over n squared. So for any given energy state, we can now figure out where the energy is. So this n is a whole number from 1, 2, 3, all the way up to infinity. No partial numbers and no 0. And the energy for this electron, or this level, we're going to, in a second, think about the energy difference between these states. So if n equals 1, this is what we're going to call the ground state. And that ground state basically is where the bottom energy well is. So in this case, we're going to look at the increasing energy. And for the n equals 1 state, we know that that is basically negative 2.18 times 10 to the negative 18 joules in this equation. N equals 2 is going to be negative 2.18 times 10 to the negative 18 divided by 4. So it's negative 1/4 HCRH n equals 3. And you can see that the difference between these states they get closer together as they get further away from the ground state. So this energy diagram is for the hydrogen atom. The hydrogen atom has 1 electron. And so Bohr's realization is that electrons can move between states, but only one state. So what we're going to try to do is to calculate the energy between one state and the other state. If it goes from 1 to 3, 2 to 4, the Rydberg equation, if you remember, has an N1 and an N2. But it's only when it goes down in energy. So we need an equation that's going to allow us to determine what happens if it needs to go up in energy. So delta E is equal to E final minus E initial, which is going to equal negative 2.18 times 10 to the negative 18, 1 over NF squared minus 1 over NI squared. This equation is how we will be able to calculate the wavelength of light, or the energy of a photon, or anything else about this transition between these two states. So when delta E is positive, NF is greater than NI. So delta E is going to be positive. You're going to put energy in to go up. So an electron absorbs a photon where E photon equals h nu, and that equals delta E. So when NF is greater than NI, when you go up, in this case, E photon is equal to delta E. I promise this does all come back together. We're just all going to go in the messy middle for a minute. If delta E is negative, NF is less than NI. In this case, an electron emits energy. Well, it emits a photon with energy, where E photon still equals h nu, but but now it's going to equal negative delta E. So if the electron goes down from a high energy state to a low energy state, this wavelength of light is directly related to this equation, but we can convert the energy change all the way back to the wavelength of light. And we can do that by realizing that there are differences. When delta E is positive, E photon equals delta E. When we have emission, E photon is equal to negative delta E. As we do examples with these, you'll realize that basically you need the sign to be positive in order for you to determine the wavelength of light. That clock has got to move. But I think, well, let me ask this. What questions do we have about this information thus far?
So what is the relationship between the arrows?
So the bottom of the arrow is where it starts, the head is where it goes. So this is an electron transition. So where we're going is questions like this, where you're provided a graphic and asked to determine the wavelength of light, or where it's going or how it's going to get there. But we are not there yet. Other questions? Okay. I think I'm getting overwhelmed vibes from all of you today. So we can all put our notes away. We are going to go ahead and think about the exam return. I'll let you guys put your stuff away before yeah. Okay, so a couple of things about your midterm exam scores. Well, I think this will work better if we all stop zipping our bags. Mostly because what I'm going to say, I feel like if you're monkeying around with your belongings, you'll be like, wait, what? So, these are the letter grades. They are the same rough scores as you see on everything else in this course. These directly correspond. Basically, it's 2 times the values for a mini exam. It's the same things. Some of you may or may not, some of you are going to be super thrilled. Others of you are going to be like, ooh, I don't like this. So, there's an opportunity for 30 bonus points. If you scored a 200, this is an opportunity for you. You may get a 230 out of 200. If you scored a 0 or a 5, you may also earn 30 bonus points. It is a Canvas quiz that I have not written. So in addition to all the other things I said I was going to do when I walk back upstairs, I'm going to do that too. So that quiz will open sometime this evening. It is due Wednesday at 4:30. You have basically 48 hours, slightly less. I can't do that kind of math this fast. It's 3 questions. They're going to be real similar to what's on the exam. Because I think one of the things I realized is a lot of you guys are taking mini exams and then being like, ooh, I don't care about that anymore. Bye. And so now, on the midterm, it felt like there was some of the information where none of you had ever seen a titration before. Or you struggled really hard on the calorimetry. So I have written all over a lot of your exams with feedback. If you have questions about that, look back at your notes. It is open notes. It's going to be like the exam. So they are 10 points apiece. There's 3 of them. When you open the quiz, all 3 of them will be there, just so you know. These are going to be primarily graded by Canvas. It's really a, did you know how to do it this time or not? Now, Canvas will have a meltdown on you if you try to add units and it didn't ask for that. So I will look over all of these later, but there's no additional partial credit. So there's different ways that you can set up a Canvas quiz. When you open this, all three of them will be on that same page. I'm not going to lock you from one to the other. It is open notes. All of your remaining exams are single person only. I would strongly recommend that you do these alone. But as always, I cannot force you to do that.
So for the quiz, is it on past things we've learned or like current things we're learning right now?
It's like the stuff on the midterm. So it is just like what you just saw. I'm going to hand you these papers. It is that I think some of you might need a second opportunity to show me what you know. It's open to all of you. I do want to be clear, this is optional. If you are like, I'm very pleased, I just don't have time for this, then you do not have to do it. If you would like to do it, please take care of that. Please make a point not to ask SI. In SI, she is well aware of this. She will not show you how to do this. That's how this works. So it is 3 questions. It says no partial credit. In my previous course, someone asked, like, so if I do, is it either you get 30 or nothing? They're 10 apiece. So you could say, I'm only going to do number 1 and just get 10 points, just get 20, or get 30. Are there any questions about this quiz? It should be open relatively soon. I mean, I'll still have to write it, so that it will not be immediately. There will be an announcement when this goes out. If your friends are not here, feel free to encourage them to do this as well. Your letter grade's reflectiveness is going to go up today. So you can see where your letter grade is for this semester. This can only help you. This should not hurt you. This is a one-time offer. We should not expect to see this really ever again this semester. Any questions?